Okay, so we got a request to do a video about partial differential equations. This request seemed to mostly be about the topic of characteristics in PDEs, so that's going to be my primary focus in this video. Before we get to characteristics, we just need to briefly recall the chain rule, which people would have learned about if they took 2415 or 2419. And we really just need to know how to take the derivative with respect to t of something of the form u of t x of t. So the chain rule would say that that would be equal to the partial of u with respect to t times the partial of t with respect to t, and then plus the partial of u with respect to x times the derivative of x with respect to t. Okay. Now, derivative of t with respect to itself is just 1. And then I rewrote the partials as ut and ux. All right, so then this is the derivative according to the chain rule. I think it's maybe worth noting at least once that ut and ux should be evaluated along t x of t. Dx dt is a function of t, so it'd be evaluated at t, okay? So to make the notation simpler, I'm not writing all of that out, but maybe that is something that's good for you to keep in mind. On to the main topic now, which is characteristics. So I'm mostly going to be focusing on partial differential equations of this particular form in the video. So u, p, and f could all be functions of t and x. Of course, u is the function that we are trying to solve for in the equation. Now here I've drawn a picture of the tx plane, and let's suppose that we have some curve in the tx plane given by the function x of t. So as we talked about just now, according to the chain rule, derivative with respect to t of u of t x of t would be equal to this. Now, let's suppose that the curve x of t satisfies dx dt equals p. And here I decided to maybe just emphasize p would be evaluated along the curve tx of t. Okay. All right, so if dx dt is equal to p, then I can replace dx dt with p up here, and that will lead to this result. And now notice that ut plus pux, that was the left-hand side of our PDE. So if u was a solution to the PDE, then that ut plus pux should be equal to f, okay? And so here we have derivative of u is equal to f. So integrating both sides, we would find that u is equal to the integral of f. So in summary, we can solve for u along this curve x of t by simply integrating the function f along the curve. Okay. So curves defined by this equation, dx dt equals p. Such curves are known as characteristics or characteristic curves of the PDE that we have here. And once again, what is special about a characteristic is that solutions to this PDE along a characteristic can be found by integrating the right-hand side f along the characteristic. When combined with an initial condition, characteristics can be used to solve the initial value problem, and I'm going to illustrate that with various examples in this video. All right. So the examples that I'm going to do are some examples that the student requested. All right. Apologies, I have a lot going on in the background. Okay. Now, before I get to the specific examples that the student requested I go over, I'm going to start with this example, which I just kind of randomly made up. So let's consider the PDE, ut minus 3ux equals 0. And we have an initial condition here. So this is when t is equal to 0. So we usually think of t as representing time. So we're saying when time t is 0, so initially, our function u should look like the sine function. All right, so here is a particular PDE. So it's of the form ut plus pux equals f. So p would be the constant function -3, and f would be the constant function 0. Now remember that the characteristics are defined by the equation dx dt equals p. So here what we can do is we can integrate both sides with respect to t. So we will get x equals -3t plus k. All right. So this is the equation of a line in the tx plane. The line would have a slope of -3, and k would represent the x-intercept in this picture. Okay. Here it's maybe worth noting, I think, that k could be, it's just a constant, so it could be any real number. So hence, we have a family of characteristic curves associated with our PDE. The characteristic curves are all of the lines with a slope of -3 in the tx plane. Yeah. Now, on the subject of what we talked about earlier, we can find the solution u to our PDE when it's evaluated along a characteristic by simply integrating the function f along the characteristic, okay? Okay, so that means when we evaluate our solution u along any one of these lines, any one of these characteristic curves, it should be equal to the integral of f, which in this particular problem is 0. And so the integral of 0 is just a constant. So what we're saying is that the solution u along any characteristic curve is some constant, which I will denote as c, I suppose, okay? All right. Now, at the moment, this maybe doesn't look very satisfactory because Ideally, what we'd want to do is we'd want to find an expression for u at any point tx in the tx plane. And what we have right now is that the solution u is going to be constant along any of the characteristics. Okay. So we can actually figure out an expression for u of tx. So let's imagine in my picture, I have a particular point tx, okay, in the plane. And then here I have this characteristic which passes through that particular point. Okay. So the equation of the characteristic is x minus 3t equals k. And because I know that u is constant along any characteristic, so I know that u evaluated at this point tx should be equal to u evaluated along any other point on the characteristic. In particular, it should be equal to u evaluated at this point where t is 0 and x is k. Okay. So what I've done is I've used the fact that u is constant along any characteristic, and by doing that, I can find the value of u at this point by traveling backwards along the characteristic until I reach the x-axis. And what I can do here is I can now use the initial condition that we had in the problem. So when t is 0, u should be equal to the sine function. So u of 0k should equal sine of k. Okay, so now we have some information about u at an arbitrary point tx in the plane, but still our answer is in terms of k. So of course we'd want an answer in terms of t and x instead. So how can we do that? Well, looking at the equation of the characteristic, we could say that k is equal to x plus 3k. Sorry, x plus 3t. So if I just plug that into this expression, then we end up with u of tx equals sine of x plus 3t. So then this would be the solution to our initial value problem. So for this example, let's go ahead and check that. So if we plug in 0 for t, then we do get u of 0x is sine of x. So our initial condition is satisfied. Okay, so that checks out. If we compute the partial derivatives, so the partial of u with respect to t would be 3 cosine of x plus 3t. Here, the partial of u with respect to x would be cosine of x plus 3t. So if we take ut and we minus 3 of ux, notice that they would cancel out and give us 0. So that in fact, this function u is also a solution to our PDE. Okay? So as a solution to the PDE that satisfies the initial condition, That means we have found the solution to our initial value problem. All right. So I'm going to do some more examples of solving PDEs, or initial value problems, using characteristics. Okay, so for the next example, let's consider the equation ut plus 2ux equals 1. Okay, let's have an initial condition. When time t is 0, u will be equal to the function e to the negative x squared. All right, so for this function, or for this PDE, p would be the constant function 2, f would be the constant function 1. So let's start by getting the characteristics. So once again, the characteristics are defined by the equation dx dt equals p. All right, in this problem, we can integrate both sides. So we get x is 2t plus some constant, which I'll call k. So then this is the equation of a line with a slope of positive 2. And it would intersect the x-axis in this picture at k. Okay. All right. So then the characteristics of this PDE are going to be the lines in the plane with a slope of positive 2. Now, again, we know that u, the solution to the PDE, evaluated along a characteristic, should be equal to the integral of f, the right-hand side, along the characteristic. So for this example, that means that u, if we evaluate when x is 2t plus k, it should be equal to the integral of, well, 1 dt. So integral of 1 dt would be t plus some constant, which I will call c. Okay, so this is what our solution looks like when we evaluate it along a characteristic. Now again, I want to get an expression for u of tx, okay, rather than u of t and 2t plus k. All right. So to do that, it'll work similar to what we did in the previous example. So here in the picture, let's suppose I have a particular point tx in the plane. And then here I'm looking at the characteristic that passes through that particular point. Now we know that our solution along this characteristic is going to be of the form t plus some constant. So first, let's kind of travel back in time along the characteristic to this initial point where t is 0 and x is k. So if we plug in 0 for t into this expression, then we will get that u evaluated at 0k should be equal to the constant c. Now, on the other hand, when t is 0, we can apply our initial condition. So u of 0k should also be equal to e to the negative k squared. So from that, we now know the value of the constant c. So what we can say right now is u evaluated along this particular characteristic, which starts at the point 0k. We know our solution is equal to t plus e to the negative k squared. So now we have a bit more information. Now, what we want to do though is we want to write our answer in terms of t and x rather than t and k. So to do that, it'll work kind of the same way as before. We just need to replace k with an equivalent expression in terms of x and t. So we can do that by going back to the equation of our characteristic. So you see from the equation that k should be equal to x minus 2t. So I'm just going to plug that into here for k. And so then this should be the solution to our initial value problem in terms of t and x. All right, so let's also go ahead and just double check to see that this solution actually works. I won't do it for every example, but maybe I'll just do it for this example one more time in the video. So if I plug in 0 for t into what we found for this solution, we do end up with e to the negative x squared. So the initial condition is satisfied. Next, let's just compute the partial derivatives real quickly. So ut would be 1 minus, I think it'll be plus 4 x minus 2t times the exponential. Ux, so if we do the partial of u over here with respect to x, it's going to be negative 2 times x minus 2t, and then times the exponential. So if we do ut plus 2ux, okay, so check it. These terms will end up canceling after the multiplication by 2, and you would just be left with 1. So our solution does satisfy the PDE as well. So that's just verifying that it is in fact a solution to the initial value problem. All right. Just a couple more examples. So next, let's consider the equation ut minus x ux equals 0 with initial condition u of 0x is 1 over x squared plus 1. So let's get the characteristics first. So again, the characteristics are defined by the equation dx dt equals p. Now in this problem, p is the function negative x. So it's not constant this time. All right, so we can solve this differential equation for x right now. So the solution should be, x should be some constant, which I'll call k, times e to the negative t, okay? Okay. So then this time the characteristics are not going to be straight lines, but this time the characteristics are exponential curves, okay? So when t is 0, x would be equal to k. So once again, k is representing the x-intercept. And then it should resemble e to the negative t, whose graph looks something like this. Okay? All right. All right, so all of these exponential curves are characteristics of our PDE. Now again, we know that the solution U evaluated along a characteristic can be found by integrating the right-hand side of our PDE along the characteristic. In this case, the right-hand side of the PDE is 0. So integral of 0 gives us a constant. So hence U evaluated along any characteristic will be constant, okay? All right. So now to get an expression for u of tx, we imagine having an arbitrary point tx in the plane. And then we look at the characteristic which passes through that particular point. In this example, we said that u is going to be constant along a characteristic, meaning that u evaluated at this point tx will be the same as u evaluated at any other point along this characteristic, because it's going to be constant there. So in particular, it'll be the same as u evaluated at the point 0k at the beginning. We can apply our initial condition to say that u of 0k will be 1 over k squared plus 1. Okay. And then finally, to get our answer in terms of t and x, so let's see. So we want to replace k with an expression involving t and x. So we can do that using the characteristic equation. So if x is equal to k e to the negative t, that means that k would be equal to x e to the t. So hence, our solution will be replacing k with x e to the t, so k squared, and plus 1. This would be the solution to our initial value problem. All right, I'm going to do another example. Let's consider the PDE ut plus t squared ux equals 0 with initial condition u of 0x equals e to the negative x squared. All right, so we're taking a look at this example next. So again, we'll start by finding the characteristics. And again, remember that the characteristics are defined by the equation dx dt equals p. In this case, p is the function t squared. All right. Integrating both sides with respect to t will give us x equals 1/3 t cubed plus a constant k. Okay. All right, so I'll draw a picture in the tx plane. All right, so here our characteristics are going to be cubic graphs. Okay, it's shifted up and starting at the value of k. It could be shifted down if k were negative, by the way, but I keep drawing my pictures as if k were positive. Okay, and then it's going to be the graph of cubic, so it'll kind of look something like this. Okay. All right. Now, since t represents time, you might have noticed in the picture I'm usually starting t at 0 and then only considering positive t's. If you did want to consider negative values of t, then of course the cubic would extend downwards like that as well. All right. So those are the characteristics. They're going to be cubic graphs. Now, once again, we know that our function u, if we evaluate it along a characteristic, so when x is 1/3 t cubed plus k, that our function u should be equal to the integral of the function f, which in this case is 0, evaluated along the characteristic. So once again, the integral of 0 just gives us a constant. So that means our solution along any characteristic is constant, okay? So now to get an expression for u at any point tx. So imagine having a point tx in the plane. And again, you want to examine the characteristic that passes through that point. Okay? Now, along any characteristic, our function u is constant, meaning that u evaluated at the point tx is the same as u evaluated at any other point along the characteristic. So in particular, it'll be the same as u evaluated at the point 0k. Now applying the initial condition, we know that this is e to the negative k squared. Yeah. All right, so u is equal to this constant value along this characteristic. And from the characteristic equation that we have here, we can say that k would have been equal to x minus 1/3 t cubed. So I'm going to plug that in for k to get my solution in terms of t and x. So this would be the solution to the initial value problem, okay? So I'm going to do 2 more examples. All right, let's do another example. So let's consider the equation ut plus 3 ux. Let's have it equal to xt this time, okay? All right. For an initial condition, let's say that initially when t is 0, u is just equal to x, okay? So first, let's get the characteristics. So let's look at the equation dx dt equals p, where p is a constant function 3. So integrating with respect to t, we find that x is 3t plus some constant, which I'll again call k. So these are lines with a slope of positive 3. Okay, with x-intercept k. So all of these lines with a slope of 3, these are the characteristics of this PDE. Now we use the fact that the solution u evaluated along any characteristic should be equal to the integral of the right-hand side of the PDE, also evaluated along the characteristic. So let's see how that works for this problem. So x as a function of t is 3t plus k. F was the function x times t. But for x, we're plugging in x of t. All right. So then here we've got some integration that we need to do. We'll get 3t squared. So integral of 3t squared is t cubed. And then we'll get plus kt. And integral of kt would be kt squared over 2. And then after integration, we do pick up another constant, c. So this is what our solution will look like evaluated along a particular characteristic. So now we want to know what u is going to equal at an arbitrary point tx. All right, so first things first is we should figure out what this constant c should be. So to figure that out, we want to use the initial condition that we have. So along this characteristic, in particular, so we know that along the characteristic, this is what our solution looks like. So in particular, when t is 0, so when we're starting at this initial point on the characteristic, when t is 0, this is going to be equal to c. All right. Now, on the other hand, from our initial condition, we see that u of 0k should be equal to k. So therefore, the constant c is actually equal to k. And then finally, to get the answer in terms of t and x, I just need to come to the characteristic equation. We can say that k is x minus 3t. So replace k with x minus 3t. And then that should be the solution to our particular value or initial value problem, okay? All right. So that problem was slightly more complicated because I made the right-hand side a little bit more complicated. So we actually had to do a bit of integration, a bit more integration than usual this time, okay? Finally, I'm going to do one more complicated example. So just to give a sense that what I've been talking about with characteristics, we can generalize it to other problems. Let's consider, let's see here. Okay, let's consider the following PDE. So ut plus y ux minus x uy equals 0. With an initial condition when t is 0, u of 0 xy is equal to e to the negative x minus 1 squared minus y minus 1 squared. So this is something new because we've added an extra variable, y, to the problem. So I'll work through some of the details of this example. I'll talk about the characteristics and whatnot. But this is just to kind of show you that the method of characteristics extends to more situations aside from the ones that we've seen up until this point. So let's examine the chain rule for differentiating something of the form u of t, x of t, and y of t. So that will look something like this. It'll be the partial u with respect to t times the derivative of t with respect to t, which is just 1. Then it'll be plus the partial of u with respect to x times the derivative of x with respect to t, and then plus the partial of u with respect to y times the derivative of y with respect to t. Okay? So that's what the chain rule will give us. Now, supposing that we were looking at a PDE of this form, all right. So if dx dt were equal to p, and if dy dt were to equal q, then we could say that this is equal to ut plus p ux plus q uy, okay? And so then if u were a solution to this PDE, then all of this we could say would equal f. Here I'll emphasize f would be evaluated along this curve, x of t, y of t. Okay. So if the derivative of u is equal to f, then once again, we should be able to solve for u along this curve by integrating f along this curve. Okay. So then that gives us kind of the same result that we saw earlier. So then these equations will define the characteristics of this PDE here. Okay. All right. So then let's try to apply that to the problem that we have here and see if we can solve it. I'm going to kind of move this out of the way. Okay. So for this problem, our p is y and our q is negative x. So we'll have, for the characteristics, they are defined by the equations dx dt equals y and dy dt equals negative x. So here we have a system of differential equations. That we would need to solve in order to find the characteristics, all right? So this system of equations, I'm going to write it, it's a linear system of equations. I can write it in matrix form. So we have dx dt, dy dt is equal to Let's see, it's equal to the matrix 0, 1, negative 1, 0 times x, y. Okay? All right, so it's a linear system of differential equations. So let's talk a little bit about that. So I'm going to call this matrix A right now. Okay. So in general, let's say that you have, let's say x is a vector valued function, and you've got a linear differential equation of this form, just like how we have over here. Okay. So the solution to this differential equation will be of the form e to the ta times possibly some constant vector c. So this is analogous to the scalar differential equation dx dt equals ax, having as a solution x equals e to the at times some constant c. Okay. So for a higher order system where x is a vector and a is a matrix, the solution has a very similar form. It's e to the ta times c. If you've ever seen e raised to a power of a matrix before, we define that by using the Taylor series formula for the exponential. So I guess I'll remind you guys of that real quickly here. So e to the x, the Taylor series formula is summation 0 to infinity x to the n over n factorial. So e to the ta, we also define it as an infinite series of ta to the n over n factorial, which I'll maybe rewrite as t to the n over n factorial times a to the n. Okay? All right. So one can prove that that series always converges. So the matrix exponential is well defined. All right. All right, so let's see if we apply that to the problem at hand. So we can say that the solution x, here I maybe emphasize x of t, y of t. So it should be equal to e to the ta, where a is this matrix that we have here. And that'll be times some constant vector c, okay? So how can we compute e to the ta? We have this series formula, but we probably don't want to evaluate the infinite series to do that. So I'm going to say a fact about matrix exponentials right now, which I'm not going to prove, but I am going to use it for this problem, okay? So if A is a matrix satisfying A squared equals negative identity, then it can be shown that e to the ta will be equal to cosine of t times the identity matrix plus sine of t times the matrix A. Right. By the way, that's somewhat analogous to If you've ever seen Euler's formula before, e to the it, where I is the imaginary number, you might have seen this is equal to cosine of t plus I times the sine of t, where I squared is -1. So this formula is somewhat analogous to that formula there. You have a squared equaling negative identity, which is somewhat reminiscent of I squared being -1. And then you have this formula, which looks somewhat similar to the Euler's formula here for complex numbers, all right? Now, I bring that up because this matrix A here, if you compute it to verify, you should find that A squared does give you negative identity. So therefore, I can use the fact that e to the ta would equal cosine of t times the identity. I'll multiply the cosine into the matrix. Right, so cosine of t times the identity, and then plus sine of t times a. So I'll multiply sine of t into the matrix A. So we've got that's e to the ta, and it's multiplying a constant vector c, which I'll now denote as ab, okay? All right. So I'll multiply this out. So here we've got just cosine t, sine t, minus sine t, and cosine t times AB equals xy. Let me drop the of t, and I'll just write xy now. So that gives us x will be a cosine t plus b sine t, and then y will be minus a sine t plus b cosine t, just multiplying these out. So these are the equations of our characteristics, okay? All right, so let's scroll up a bit. So now that we have found our characteristics, what are we going to do? Well, we're going to use this fact again, that our solution to, or the solution to our PDE, evaluated along the characteristics, will be equal to the integral of the right-hand side of our function, of our PDE. So u evaluated at t, and so this is x of t, this is y of t. So I don't want to write all of that out, so I'm just going to write x of t and y of t for it. So it's the integral of the right-hand side, which was 0 in our PDE. So in other words, our solution along any characteristic is going to be constant. let's word it like this. So yeah, u is constant along any characteristic. Okay. So again, we want to get an expression for u evaluated at an arbitrary point t, x, y. So to do that, it's a little bit hard for me to draw the picture, but let me maybe try to give a picture here, okay? This time I think I'll put t in as the vertical axis. Now, the equations of our characteristics over here, okay, these equations are going to trace out a curve in x, y, t space, all right? I don't know exactly what it's going to look like, but because I see cosines and sines, I think it's going to be maybe sort of it might actually be somewhat elliptical. Well, so this picture is maybe not accurate, but I just want to draw a generic picture right now, okay? So this is not necessarily pertaining to our specific problem per se. I just want to give you guys a sense of what's going on by drawing this picture. So let's imagine we have a particular point t, x, y in space. And then let's suppose this was the characteristic curve that passes through that point. And when t is equal to 0, so when we're in the xy plane, this would have been the initial point of the characteristic, okay? Now, we are saying that u is constant along a characteristic. So u evaluated at this point txy should be equal to u evaluated along any other point on the characteristic, since u is constant. In particular, it'll be equal to u evaluated at this initial point. Okay. So here, these were our characteristic equations, okay? So when t is 0, x would be equal to a, y would be equal to, when t is 0, y would be equal to b, okay? All right. And then, okay. We can now use our initial condition. So when t is 0, all right, up here. When t is 0, we know that u will be equal to this exponential. So we have, we're plugging in a for x and we're plugging in b for y. So that will give us e to the negative a minus 1 squared minus b minus 1 squared. So that's what our solution looks like in terms of a and b. But again, we would like to have our solution in terms of the actual variables x and y and t, okay? So to do that, we would need to solve for a and b in terms of x and y. So let's go to our characteristic equations up here. I think this time I'll actually copy it and paste it. Okay, so let's try to solve for a right now in this equation. So if we multiply both sides of the equation by this first equation by cosine first, we'll get x cosine t is a squared, or sorry, a cosine squared t plus b cosine sine. Likewise down here, I'm going to multiply this equation by sine, so that y sine t will be minus a sine squared t plus b cosine sine. So if we subtract these equations from each other, we'll cancel out the b's. Here we'll end up adding. And if you factor out the a, you get cosine squared plus sine squared, which is 1. So it'll just be a times 1, so it'll be a on the right. So a is equal to x cosine t minus y sine t. Okay? Likewise, we can solve for b in a similar way. If you multiply the x equation by sine, and then if we multiply the y equation by cosine, and then we add these equations together, that would eliminate the a's. Here, after you factor out the b, you'll get sine squared plus cosine squared, which is just 1. So it's going to be b equals x sine t plus y cosine t. So finally, we can plug these expressions in for a and b up here, and that will give us the solution to our initial value problem in terms of t, x, and y. So it's going to be e to the negative a minus 1, and then minus b minus 1 squared. There you have it. That is the solution to our initial value problem, okay? So you can actually check by plugging this into the PDE and seeing that it satisfies the PDE. And you can also check that it satisfies the initial condition, all right? So those are all the examples that I had regarding or illustrating how to solve PDEs using characteristics. 2 of these examples were kind of ones that I made up on my own. The other examples were specific requests by the student who requested this video. Now, there were some other exercises that the student requested for me to work through that did not really involve solving equations using characteristics. So for that student, I'm just going to go over those examples at the end of this video now. So this is no longer about characteristics. This is just me doing 2 examples which were requested by the student. So the first example was actually an extremely simple PDE. It was just du dt equals x. So you can solve this PDE just by integrating both sides with respect to t. Now here, x is being treated as a constant when we integrate with respect to t. So it'll just be xt. And then since we integrated, we pick up a constant. But that constant will actually possibly be a function of x, since we were treating x as if it were a constant, okay? So this will give us the general solution. To this differential equation here. We can quickly check that it works by computing the partial u with respect to t. So that would just be x here. And since this is just a function of x, the partial with respect to t would become 0. So therefore, this function u does in fact satisfy our PDE. Okay. Without any information about an initial condition, we do not know what the function c of x is. But of course, if you were given an initial condition, say if t is 0, then u is some function of x. Then over here, if we plug in 0 into our general solution, this term would 0 out, and you would just get c of x. So therefore, c of x would have to have been equal to whatever your function g of x was in this initial condition. And the solution to the initial value problem would then be xt plus g of x. Okay? All right. All right, and then the other example that the student wanted me to work through was this question, which is from a textbook. All of the requested exercises were from a textbook, actually, which I think I'll go ahead and maybe post a link to that book in the description of this video, just if anyone is interested in it. So we have this PDE, and we're given an initial condition that u of 0x is just some function f of x. We're told that we can assume that f is C1, meaning its derivative exists and is continuous. We're also told to assume that f is bounded. Now, for this problem, there were 3 parts to it. So part A was if f is greater than or equal to 0, to show that u is defined for all points tx, and that the limit as t approaches infinity of u of tx for any x will be equal to 0. That's part A. Part B is if f is strictly negative, then there will exist or let's write it like this. Then for each x, there exists a number which I'm going to call, well, I'll just use t. So this is t, a real number t, so in particular there exists a finite time, if you will, for which u of tx is undefined, and the limit as t approaches, okay, so I'll use tau for this particular time, and such that the limit as t approaches tau from the left of our solution will equal negative infinity. So roughly, statement B is saying that your solution blows up in a finite time, is kind of what the statement B is saying. And then C was just asking, what is the longest interval 0 to tau for which u of tx will be defined. For t between 0 and tau. And I think it's the longest interval among all x's. Okay. All right, so that's kind of an interesting problem. So let's see how we'll approach it. So first, we can actually solve this PDE directly without doing anything particularly fancy. So from this PDE, let me rewrite it as partial of u with respect to t. Whoops. Equals negative u squared. All right. So we can basically treat this as if it were an ordinary differential equation. If we separate by moving the u over to this side, and if we just sort of, looks like we're multiplying dt over to here. This is what we did for separable equations in ordinary differential equations. And then we integrate both sides with respect to t. Or rather, we just integrate both sides, rather. So here, integrating u, negative u to the negative 2 with respect to u would be u to the negative 1. And then integrating this with respect to t would give us t plus some constant. And again, here, since we were integrating with respect to t, that constant could really be a function of x, since we were treating x as if it were a constant, okay? So 1 over u is t plus c of x. So therefore, u, our solution, has the form 1 over t plus a function of x, okay? So that would be the general solution to our PDE. Now I can solve for the function c of x by using the initial condition. So when t is 0, u should equal this function f of x. Plugging 0 in for t into our general solution gives us 1 over c of x. So therefore, we can say that c of x is 1 over f of x. Okay? So I'll plug in 1 over f of x into c of x here for the general solution. So that means our solution to the initial value problem is going to be 1 over t plus, and then c of x was 1 over f of x. And to simplify this, if you just multiply numerator and denominator by f of x, multiplying the denominator by f of x will give us t f of x plus 1, okay? So that is the solution to our initial value problem. And now we can use it to answer parts A, B, and C. So for part A, if f is always greater than or equal to 0, then our denominator will always be strictly greater than 0, since we're always adding 1 to it. So it's always going to be greater than or equal to 1. Whoops. Okay. So the denominator of u is going to be greater than or equal to 1. That is why u will be defined for all values of tx, because the denominator will never go to 0. Then the limit as t approaches infinity of u of tx. So you can see as t goes to infinity, the denominator will blow up, go to infinity, and so that will drag everything down to 0. So that's what's going on in part A. In part B, if f is less than 0, then we've got a problem because the denominator will be equal to 0 when t is negative 1 over f of x. I guess we should specify t since we're thinking of t as time. We really are assuming in this problem that t is going to be greater than or equal to 0, okay? So since f is negative in part B, this is a positive time t. So for this time t, this would be the time tau, which is kind of referenced in part B. So u evaluated at this time tau and x would be undefined because the denominator would be 0. And if we think about the limit as t approaches tau from the left, basically as t approaches tau from the left, the denominator is going to approach 0 from the negative side, and that's why it blows up to negative infinity. Okay? All right, and then lastly, for regarding part C, so we know that our function has a singularity when t is negative 1 over f of x. So this expression will be maximal when, by the way, C is still assuming that F was negative, so it's a continuation of B, if that wasn't clear. All right, so this expression is maximal when F is as close to 0 as possible, because that would make the denominator as small as possible, making the thing as large as possible. Okay, so this is maximal when f of x is as close to 0 as possible. And since f is negative, by assumption for this part of the problem, that means it's maximal when f is as close to 0 as it could be. That will actually be its maximum value. So I guess what we could say for this part is if, let's say that f evaluated at some particular value of x, maybe I'll use, let's say if f of a is the maximum value of our function f of x, assuming such a maximum value exists, then we can say that when x equals a, u will be defined on the interval from 0 to the time -1 over f of a, and that for any other x, the time interval that u is defined on will be smaller or shorter than this interval, (0 to -1 over f of a. All right, I'm going to end my video with that. Oh, well, okay. I might do another video talking a bit more about characteristics, in particular looking at some cases where the method of characteristics maybe doesn't work so well. I'll also maybe look at some more complicated PDEs, which are non-linear, and we'll see some of the subtleties of that and using characteristics to solve them. I might do a video about that.